getting the Bessel's functions, Bessel's differential equations. So that is once, and here of course NR will be there, right? K square in one square it is there, but this time it is K square minus beta square. This factor will be there, right? In case of GI fiber, right? Otherwise it is same. Now, as per WQB method, we have seen this phase function. You can assume the solutions, and if you solve it with the power series of QR, that is these ones, then and equating the coefficients on both sides of K square, then what you will get it? You will get this KQ0. That is, this one will get it, and the modes will be bounded if this is real. Q0 is real. Q0 is real between the 2 points around R2 within the core of the fiber, and beyond these regions Q0 imaginary, right? So the mode is bound if Q0 is reals. That is the condition. That's what is shown here in the curve. You have seen it. The two caustic surfaces are there where this is R1 R2 range. This is R1 R2. You can see it R1 and R2 within this range. Q0 real, right? That means energy is trapped not throughout the core, rather it's in certain region within the core, which is not true for SI fibers. And we have seen this in the ray trajectory, skew ray analysis. We have seen this rays are turned after certain points. That points actually called the turning points. That is actually decided by R1 R2, right? And the locus of these turning points are called the caustic surfaces, right? And how will get this R1 R2? If you this the intersection of these two expressions, K square inner square minus beta square and mu square by R square. You'll get this R1 R2. Once you get this R1 R2, the upper limits, then you can solve these equations. This in another concept to have considered within these regions, actually it will form a standing wave like patterns, right? And the ray actually interfere itself constructively. For this, the condition is Q0 must be m pi. So if that is the case, then you see it here, m beta we can write in this form. So this factor we have seen it for because of the polarizations. If we have m nu polarization, there will be 4 kinds of different polarizations, right? Anyway, after solving all those things we have seen last time, so ultimately we'll get the number of modes in GI fibers. It is alpha by alpha plus 2 a square K square n square delta. Alpha is a, we have seen it, it is the parameter that determines the shape of the profiles. Generally, if alpha is not mentioned, you can assume alpha equal to 2. That means the parabolic profiles. Right? A is the fiber core radius. K is the propagation constant 2 pi by lambda. N1 is the refractiveness of the core, and delta is the fractional index difference, that is N1 minus N2 upon N1. Right, and if alpha equal to infinity, I told you these relations will convert into SI fibers, modes in SI fibers. Right, so these things we have seen it. Of course, here also some more things are there, but single mode conditions in GI fibers. But if you are interested, you can go through the GI senior fiber. One book is there, senior. Also available in internet that you can see it. Next, you see the attenuation in GI fibers, right? Attenuation in attenuation in SI fibers, in optical fiber, rather in optical fibers. In GI SI common, the attenuation is common all types of fibers, right? And this is an important parameter, attenuations, because this actually determines the repeater distance between transmitter and receiver, right? And this, if you launch some light, then that energy will not be same at the output end of the fiber, because it is optical signal. So there will be absorption, scattering. These factors will be there, and they will degrade. I mean, power will be attenuated. Right. Also, there will be radiation loss, absorption, scattering, and radiation loss will be there. That they will attenuate, and these factors will attenuate the signals. I mean, if you launch some power will be less at the output end of the fiber. Suppose if P in is the input power and P out is the output powers, Then you see the loss in dB. It is dB by m. If there is a logarithmic scales, it's a ratio. It is 10 by L log of P input by P output. Log 10 base here it is, right? So it is, and sometimes in absolute measurement, this is relative unit dB. In absolute scale, absolute measurement also you can have a dBms. That is 10 log P by 1 million. With respect to 1 million also, you can calculate dBms, right? And the loss or power can be expressed in terms of dBms, right? Say 0 dBm means corresponds to 1 milliwatt. So with respect to this, also another unit is used to describe the power, right, or loss. So, but this is generally used alpha. This is another important parameter of optical fibers. So we have seen numerical aperture, one important parameter, V numbers. Now alpha is another important parameter of optical. Actually, when you procure the fibers, if you want to use the fibers, these three are most important. Of course, bandwidth also is there. Bandwidth, that means type of fiber. You have V number, will identify the type of fiber, but still, say certain it is multimode fiber. Then also you have to see what is the bandwidth of the fiber. So these are the important parameters while dealing with the fibers, and these are important relations while concerning the attenuations. Now the question is, what are the attenuation mechanisms? Say absorptions, there are different kinds of absorption. Scattering also, there are different types of scattering. Radiation also, what is the cause of radiations? Now we'll see in the details of all those things, right? Just a minute, let me see how many of them joined so far. Okay. 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 So we'll see now in details. Let me consider the next slide, next PPT. This is not. Subodhan, it is visible?
Yes, sir.
Okay. This actually in your quiz, attenuation and another signal distortion will be there. This is signal degradation, signal distortion would be there. I mean, in the first modules. So now we are discussing now attenuation. So you see it here, just now mentioned, they are the causes for attenuation, absorption, scattering, and radiation, right? And also you have seen this, how the attenuation quantitatively you can measure alpha in dB per, it is dB per kilometer, keep in mind, 10 by L log base 10, it is P input by P output. Actually output by input, but a negative sign will be there. So that if you just input the negative sign, then it will be P input by P output. So that is the most important. Alpha, it is dB per kilometer, and L, it is in kilometer, right? So these things to keep in mind. Now see the causes. So there are three main causes for attenuation. One is absorption, another is scattering, another is radiation loss. Right. First, if you consider the absorptions, these the several factors are there for that will cause, since it's a signal, it is not the electrical signal. So light signal, when it propagates, obviously absorption or scattering would be there, right? And if you consider the absorption, there are several causes are there for absorptions. There can be atomic defects. There can be extrinsic absorptions, and there can be intrinsic absorptions, right? Intrinsic absorptions, atomic, because of atomic defects. Extrinsic absorption will be, that is actually due to impurity ions. Extrinsic absorptions is extrinsic, that is due to impurity. You see, there are different impurity during fabrication. There will be different impurity ions will be there. So atomic defects. The causes are atomic defects, intrinsic absorption. These two are intrinsic absorptions, intrinsic absorptions, and there is the fourth one is the extrinsic absorptions. So there are three main causes: atomic defects, intrinsic absorption, and extrinsic absorptions. Now, if you focus on the atomic defects, this is because of missing. There can be atomic defects can be because of what is the causes of atomic defects? Because of missing molecules, high density clusters of atomic groups, or can be oxygen defects in the structure, right? So they are the causes for atomic defects, right? Because basically it is imperfections in the atomic structure. That may be atomic structure, that may be because of missing molecules or high density clusters of atoms, atomic groups, right? Or maybe oxygen defects. These are the reasons for these atomic defects. But of course, these atomic defects, losses due to these atomic defects, it is negligible compared to these extrinsic or intrinsic assertions. It is negligible. That's what is mentioned here. Negligibles, right? It's very negligible. But of course, it is significant if you consider, if you place the fiber in some nuclear radiation field. If there is in the environment, and if there is some nuclear radiations, sufficient nuclear radiation is here. Let's say, for example, nuclear reactor. Then of course you have to consider this loss. There can be atomic defects, and that will cause significant loss in the optical fibers, right? So, but in conventional case, it is generally negligible compared to intrinsic loss and compared to the extrinsic loss. Now, in intrinsic loss, you see, intrinsic loss may be intrinsic absorptions may be due to UV tails, ultraviolet absorption tails, or can be infrared absorption tails. Right. These two are actually intrinsic material absorption loss. Right. And third one is this is because ultraviolet tail. It is because actually because of the transition of electrons from, whenever there is a transition of electrons from the valence band to the conduction band. In fact, in fiber, silicon oxide is here. Silicon oxide, so oxygen molecules are there. The oxygen molecules, they are having they are very tightly bound electrons are there, and but when light propagates, then you see, if the photon energy is sufficient, then there can be a transitions from electrons from the valence band to the conduction band. So this will lead to absorption whenever there is a transition from electrons from valence band to the conduction band. And if you consider these oxygen molecules, they are just telling you that the valence band, the band gap, it is around band gap around is quite high. Let me check it. This band gap, it is here. I have written it. 8.9 electron volt. You see, oxygen molecule, oxygen ions. Silicon oxide, so oxygen ions will be there, not molecules, oxygen ions, right? Oxygen ions, they will have the band gap of the order of Eg, and of the order of 8.9 electron volt. So very high band gap is there, but photon energy is high. Then when it will be high? When about ultraviolet, you see, if you see the ultraviolet, high frequency H nu, photon energy, it is H nu. So frequency, if it is very high, that is during not in the infrared, in the ultraviolet regions, frequency is very high, so energy will be very high. So because of this high energy, for high photon energy, the electron can be excited from the valence band to the conduction band, right? And that times it will cause the loss. right? That is the reason for UV tail. But of course, these absorptions decrease when you consider the longer wavelengths, I mean low frequency regions, right? So in the infrared regions, this tail will be reduced. Ultraviolet absorption will be reduced, right? Reverse will be there in case of infrared tails. In case of infrared tails, the absorption will increase if you go beyond far infrared. It will start ultraviolet. It is almost zero, but in the infrared regions, it will have significant effect. And what is the reason behind this infrared tails? That is actually because of the vibrational molecules, right? Um, you see here, of course, the infrared because the molecular vibrations. That is because of the molecular vibrations. This um, infrared tail will occur, and the peak occurs at 8 microns. Peak occurs 8 microns. In case of UV tails, the peak occurs at whenever ultraviolet wavelength, it is around 0.14 micron. That depends on this band gap, right here, band gap, right? So these are the causes for UV tail ultraviolet absorption tails and the causes for infrared absorption tails. Right. I'm showing the car. It will be more clear for this tail. You see, this is the spectral attenuation curve. Spectral attenuation curve. This is the attenuation. X-axis is the lambda in microns, showing all the wavelengths. Wavelength means it is these shorter regions and the longer regions. You see, these are wavelength interest in optical fiber communications, 0.8 to 1.6 micron regions. Of course, middle portion it is not used. The shorter region because sources available in the shorter regions up to 1 microns, and also it is up to 1.3 micron. Also, it is there for next generations. Initially, sources are available in the shorter regions. I told you. Next window it is around 1.3 microns, and next generation it is 1.55 microns. So in this way, optical fiber technology develops, right? So you see it, what is this infrared absorption tails and ultraviolet absorption tail? This is the ultraviolet absorption. This is the dotted one. This dotted one is the ultraviolet absorption. Harshvardhan, the curves are visible?
Yes, sir.
Okay. You see, this is this dotted ones. This is the ultraviolet absorption tails. This one I told you. This is because of the transition of electrons from the valence band to the conduction band. When photon energy is quite high, that means in the UV regions. You see, UV regions it is increasing. Ultraviolet region 0.14 micron maximum peak will be there, but gradually decreases if you go on the longer wavelength side. But in the contrary, if you see the infrared tails, it is increasing in the far infrared regions. It starts at around 1.3 microns and gradually it is increasing. But in the short wavelength side, it is zero, and that is because of the this infrared tail, because of the molecular vibrations, right? Because of molecular vibration, this peak will occur, and peak it occur at 8 microns. In this case, peak occurs at 1.14 micron ultraviolet tails. Right. So there are the two tails, absorptions, intrinsic absorptions, intrinsic material absorption. One is due to ultraviolet absorption tail, another is due to infrared absorption tails. Right. Now, next, you see the extrinsic absorptions. Extrinsic because of the impurity ions. Extrinsic, this term is used because of impurity. And during fabrications, apart from this, the convention of silicon tetrachloride, etc., those things are there. Sometimes metal impurities will be present, right? Unwanted metal impurities, silica that contains also dopants are there, as well as in silica dopants are introduced to change the refractive index, as well as also some metal impurities may be present. These impurities, they shift the absorption tails both in the infrared regions, in the shorter region. I mean, UV tail will be extended as well as infrared tail also will be extended because of these metal impurities. What are these metal impurities? You see, there can be ferrous. I just mentioned. You see it here, ferrous Fe2 plus. Here it is, Ap2 plus, Ap2 plus. This is chromium ions, ferrous and chromium ions. These things will be there, right? Other metal will also can increase the absorption loss, right? These ones, right? They are the dominant metal impurities present during fabrications. Um, Apart from that, also there can be another type of impurity, that is OH ions. Problem will be there because of hydroxyl ions, OH ions, right? During pressure, hydroxyl ions will be there, and because of this hydroxyl one, I mean these are known as actually water peaks, water, and it is prominent in the 0.14 micron regions, this OH ions. And so this curve, you see it here. So OH ions, it is some peaks are there, small peaks are there at 0.9 to 1.0 micron regions, and there is 0.1, 0.2 to 1.3 micron regions. But the most prominent peak because of hydroxyl ions, it is at 1.4 microns, right? Prominent peak is there. So care must be taken to, if you want to use these opening regions, then you have to reduce this hydroxyl ions. And during fabrication, you have to take care of these the contaminants, right? These impurities should be minimum, right? So these are the causes. These are the causes for the extrinsic absorption, right? So we have seen it, this intrinsic absorption because of EBTL, infratel, and extrinsic absorption due to impurity ions, maybe because of dopants, because of metal impurities, etc., etc. So this is all about these absorptions. Of course, some more things is here. If you quantitatively, there is qualitative descriptions. Quantitatively also, you can calculate the loss due to EBTLs. You see it is the expression is here, alpha UV at an instant. It is CE. Let me check it whether it's correct. C, yes, CE. This is the constant term C E by E0 minus CE by E0, right? No, this is one expressions, right? This is one. This is for UV. This is an empirical relations, empirical or the field experience, etc. Right, developed by scientists. Alpha UV, that is CE E by E0. Here C E0 the constant, and E is the this E is the photon energy. These two are constants, right? So E is inversely proportional to lambda, E equal to HC by lambda, H nu, HC by lambda. So inversely proportional to lambda. So ultraviolet absorption decreases exponentially with if you increase the wavelength. That's what we have seen it. UV tells you see that it decreases exponentially if you increase the wavelength of light. All right, and some that is UV. Some other expressions are also there, but I'm just showing one expressions. Another expression is for infrared tell, empirical relations, infrared absorption tell, that is alpha IR. You see it alpha IR, that is 7.81 into 10 to the power 11 into exponential minus 48.48 by lambda, right? So that is the relation for infrared absorptions, right? This is also empirical relations, right? So these are the quantitative, quantitatively you can estimate the attenuation because of these infrared tails and alpha UV tails, right? Next we consider the scatterings, right? Scattering, light, whenever light propagates, there will be absorption, I have mentioned. Also, you cannot avoid the scatterings. And the scatterings generally, because of inhomogeneity, but in optical fiber, because inhomogeneity always will be, it is not the perfectly homogeneous. So inhomogeneity will be there, inhomogeneities will be there, structural inhomogeneities, right? And that will homogeneities or compositional fluctuations or inhomogeneities means structural defects. Some defects, some compositional fluctuations, or can be material density variations would be there. There's actually glass. If you just consider glass is a very complicated structure. If you see the glass structure, then sometimes somewhere you will see high refractive index, somewhere you see lesser refractive, high density, lower density, like these things because of the complicated structure of the glass, right? It's a network of molecules, glass, right? And also glass is, you see several oxides are present in the silica. Some dopates are present, germanium oxide, silicon oxide, phosphorus, etc. So these may cause the compositional fluctuations, right? Composition fluctuations will be there. There can be material density variations will be there. Also, there can be structural defects during manufacturing, during fabrication. This will be there. So these causes actually the variation of refractive index within the, even the density variation is there, density variation is there, then refractive index variation will be there. Apart from the density variations, other components are also there, compositional fluctuations, structural, these things are there. All these actually will cause the refractive index variation within the fiber, right? And if the refractive index variation occurs within a distance of the order of lambda, then scattering will result, and that scattering is called the Rayleigh scattering. In fact, if you see the scattering electromagnetic also, you can see a Rayleigh scattering would be there. Apart from the Rayleigh scattering, there can be another scattering, is there Mie scattering also there, right? That depends upon the particle size. If the particle size less than lambda by 10 of this order, less than or equal to lambda by 10s, then it is actually the Rayleigh scattering in regions. And if the particle size greater than lambda by 10s, then it is the Mie scatterings, right? Mie scattering results in the forward, it's a forward scattering process, right? So these things are there, Rayleigh scattering and Mie scattering. Achha, in this context, can you suggest to anybody why this, the red signal is used for danger signals? And can anybody suggest why red signal is used for danger signals? Can anybody suggest?
Sir, we can see red wavelength more far than other wavelengths.
Yes, that's true, but why? Yeah, rightly you have mentioned, absolutely right. But why? Or I'm giving the hints. You have this in the blue sky. Why the sky is blue? They are related. Why the sky is not red? Sometimes, of course, red, but why not other colors? The blue is, you have seen, other side of the sun uh, uh, is the blue sky. These are related. You think about it quickly, you can answer it. Anybody else? Yes, he has rightly has mentioned. You can view it over a long distance red. That's why red is used as the danger signals. But what is the cause? Anybody? No, no one is suggesting. I've seen Sahil or another. Uh, any other? No, actually, yes. I have what I'm discussing scattering. Obviously, if the scatter, if the light is scattered, then it cannot be viewed over a longer distance. Am I right? So scattering is less in case of red. Am I clear or not? Scattering is
Yes.
less for less. Or the opposite is true for opposite, say blue sky, that means indigo side, is the ultraviolet side, the scattering is more. So more, that's why you can see the blue sky like these things, right? Indigo side or Vibgyor, you see the violet side, scattering will be maximum. That's why you can see the, of course, directly through the towards the sun, you can see some other white like that is of course because of polarization. Some other aspects are there. I'm not going to the details. Just I'm mentioning the conventional things. Uh, so scattering is an important factor while dealing with these signal attenuations, right? And you see the Rayleigh scattering occurs on the particle size. You have seen the rainbow. Those are actually because of these molecular scattering, Rayleigh scattering, molecular scatterings, scattering phenomena, right? And because of the scattering, you're observing the different colors, right? Um, so water particles actually water scattering because of molecular particles. So, if you consider the scattering induced attenuations, this is another relation is here. Developed. The relation is developed for the Rayleigh scattering. It is very complex because glass is very complex. This has been developed. That is 8 pi q. 8 pi q. Carefully, you can note it. 8 pi q by 3 lambda to the power 4 into n square minus 1 whole square kBt beta. Right. So lambda is the wavelength of light in the refractiveness of the core. Kb the Boltzmann's constant. T the temperature constant. Right. Just a temperature, which actually is the temperature at which the glass solidifies. This T temperature T, and beta is the isothermal thermodynamical parameter. This beta it is called actually isothermal compressibility of the materials. Right. So these are the parameters: Boltzmann's constant, temperature, and the thermodynamic parameter, isothermal compressibility. The important factor is the Rayleigh scattering. You see it alpha, it is inversely proportional to lambda. Right. So if lambda is less, that means ultraviolet scattering will be maximum. That's why blue sky I just mentioned. If lambda increases, so longer wavelength side, red is a VIBGYOR. If you see the VIBGYOR, visible light, then you see red, it has longer wavelength. Lambda is more, that's why alpha is less, that's why it is the danger signals. Anyway, so the important factor you must note in case of optical fiber, alpha inversely proportional to lambda to the power 4. Of course, these relations, other relations are also there. I'm just showing one relations. For different components of glass, multi-component glass, it will be different. Some complicated relations will be there. So another, so we have mentioned this. We have seen this. Initially, you see it here. Absorption, scattering, and also there will be radiation loss. So we have discussed now absorption loss, scattering loss. Now another type of loss is here, that is the radiation loss. Here actually, because of this loss, radiation loss occurs. The radiation loss. This is the radiation loss. This is because of bending. If during layout of the fiber, you cannot give the guarantee the fiber always be straight, though it is within the cables, but still some bending always will be there. And if the bending is greater than the certain critical bending, then loss will be significant. So to categorize these ones, you see the bending can be of two types. It can be micro bending, it can be macro bendings. What is this macro bending? Whenever you see, whenever a fiber is bent, then this is, if this is a radius of curvature, you see this R. This is the radius of curvature. Radius of curvature. This is radius of curvature, and this is the fiber radius. This is the fiber radius. Say A. So when the radius of curvature is greater than this the fiber radius, then it is called the macro bending, right? That means when R greater than this the fiber core radius, then it is called the macro bending. But when it is R nearly equal to A, then it is the micro bending. We'll see micro bending later on. First, you see the macro bending. So in this case, say for I think you can tell me for straight fiber, what will be the value of R for straight fiber? If the fiber is straight, what is the value of R? Anybody? Then no one is responding except you. For straight fiber, what is the value of R? Yes, it is
infinite, sir.
Yes, exactly. It is infinite, right? So for other than this, so there will be certain bending will be there. So certain finite value of R always will be there. Right? That is a macro bending. Now, because of these things, why loss will occur? You see it here. Of course, from ray optics, quickly you can say whenever total interpretation condition will not satisfy, it will reflect it out. But for single mode fiber also, in general, if you see the way optics, then that can be used for single mode or multi mode. Say for if you consider a particular mode, say fundamental mode, if you consider, it is very similar to Gaussian mode. We have seen it, right? Yeah, for a straight fiber, you see, it is like these things. There are different modes are there, fundamental mode, hierarchical modes, whatever may be the case. So there is a field tail at the cladding regions, right? And now field tail in the cladding regions, you see it here. Some portion of the wave will propagate in the cladding, and some portions, maximum will be in the core if it is a single. I mean, whether it is multi-mode, single mode fiber, percentage will be more in case of core. Now, if certain bending is there, then you see the certain bending is there, then you can see it. Suppose if these are destinations, then the distance from this side and distance from this side will be different. You just see it here. And that means if the two portions of light from the light, the mode, I mean, the same mode, suppose you have launched some light, that will be in terms of mode, it will distribute down different modes. The same mode distribution will be there. Suppose it is this AG1 mode, Gaussian mode, Gaussian distribution mode. Then same mode you can have it here. In this case, the same mode structure you can have it if this portion will travel greater velocity than this portion, because the distance is large. So you see, this portion should travel greater than the velocity of this portion, right? That means light, it has some velocity, right? That velocity cannot be greater than the velocity of light, right? So after a certain distance, critical xc, you see a certain distance, okay, same, but after a certain distance, it has to be moved faster than the portion of this portion of this light. So after a certain critical distance, you see, because of this, it has to move faster than the velocity of light, which is impossible. So the mode structure will not be present. I mean, some loss will be there because of this certain critical bendings, right? For small bending, loss will not be too much, but after certain critical bending, then loss will be too much. Of course, in case of this single mode I have just mentioned, but for many modes, if many modes present, then if certain bending is there, bending, of certain critical bending, then higher order modes, they will be reflected out, right? So that is because the after a certain distance, xc, there is a critical distance from the axis of the fiber. This tail of the fiber, this field tail should move. This field tail should move faster than the this tail, this portion of the mode, which is not possible. So this will be energy, part of the energy will radiate away. So the reflected out, that means loss will be there. So that means if you consider a certain bending, then for bending fiber, suppose if it is straight fiber, certain number of modes, suppose 50 modes are there, and if certain bending is there, then you will not expect 50 modes, and less than 50 modes will be there. So that's what it is for GI fiber in general. It is mentioned here. These relations developed from the geometry. You can I will go into the derivation of these ones, but from the geometry, these relations can be obtained. Effective number of modes in GI fiber, it is n infinity into 1 minus alpha plus 2 by twice alpha delta twice a by r plus 3 by 2 into kr whole to 2 to the power 3. These ones, right? This is the relations for number of modes in a bent fiber. This bent fiber. Ineffective. What is ineffective? It is the number of modes in a straight fiber. GI fiber is taken because this is a general distance. Alpha equal to infinity, it will be converted into SI fibers. So this is the actual number of modes we have seen earlier. But in case of bending fibers, it will be reduced to these ones. So it is 1 minus something. So obviously, less number of modes will be existing in case of the bent fiber. So this is the reason for the macro bending because of these various because the field tail distributions, right? I mean because of the bendings, so longer distance will be there for one portion of the tail that has to move faster than the velocity of light, which is not true. So loss will be there. Another key I told you, this is when R greater than A, but sometimes you can have the radius of curvature, it will be same as A. Where suppose within the cable fibers, within any cable you can see BSNL or Reliance, there can be 6 to 12 fibers are there. Some spiral fashion is here, right? So within the cables, you see fibers can be bent, like if some uneven pressure is here, there can be during layout some uneven pressure maybe on the cables. Because of this pressure, then there can be some bending will be there within the fiber. So you see it here. This is the bending radius. I mean, this is the radius of curvature, and this is the fiber core radius. So in this case, fiber core radius, it is almost nearly equal to radius of curvatures. So that is the case of micro bending, right? In case of micro bending, the same concept is used. I mean, if you launch some power that will distribute among modes, so because of this micro bending, some of the modes will be radiating, right? Some of them are radiated out. So number of modes will be less, obviously power will be less, right? And this micro bending can be reduced, of course, if you use some compressible jacket. Whenever uneven pressure is there, the jacket will be distorted, but within the fiber, there will be no such pressure. So fiber will remain straight. So by using compressible jacket, you can avoid this micro bending and the corresponding losses. Another class of loss is here, that is core and cladding losses. That is not mentioned initially. Here, this loss also you have to consider when you consider the signal degradations. Signal degradation, not signal distortion. These two things you must keep in mind. Signal degradation, that is because of different attenuation degradation. And there is signal distortion. Right, signal distortion. These two are different. Distortion. Right. Signal distortion we'll see next time. So we are discussing a signal degradation. Means power is attenuated, power is degraded. But signal distortion, if you launch some pulse, that pulse shape will be distorted. Maybe broad, maybe narrow, like this thing. That is distortion. So here you see another loss will be their core and cladding losses. That is because of the attenuation coefficients alpha that will be different within the core and within the clad. If a fiber, if you see core and clad, there are different effective index N1 and N2. So different materials are there. So because of these things, alpha 2 and alpha 1 will be there. And so because of these different attenuation coefficients, there will be loss. And the loss for a particular mode of order nu n's, alpha nu n, that you can write it because of this alpha 1 p core by p plus alpha 2 p clad by p. These things we have seen it, p core p clad by p, we have seen it 430 minus half. So this can be considered 1 minus p core by, so p clad by p, actually 1 minus p core by p, right? Or reverse, p core by p is 1 minus p clad by p. So in this way, you can convert this one, and you can simplify this one. This is another loss. This is for step index fiber. For GI fiber, it will be slightly different, because in this case, n is a function of r. So in this case, alpha r, actually it is alpha 1 plus alpha 1 plus alpha 2 minus alpha 1 into n0 square minus nr square, n0 square minus nt square. N0 means when r equal to 0 means at the axis, right? Alpha 1, it is at the axis, and alpha 2 at the clad, right? So if you consider this one, then you will get the attenuation in GI fiber alpha r. And this is for a this GI, actually for a particular mode, for a given mode, this alpha GI, alpha will be this alpha GI, that is 0 to infinity alpha r. If you just infinity alpha r, PR r dr by 0 to infinity PR dr, right? This PRDR actually, this is the power content in the mode at R. This is the power content in the mode at R. So by using these relations, you can have the estimate the loss in the core and cladding losses in GI fibers. So this is for the GI fibers, and earlier it is for the SI fibers. So this is all about these the attenuations. And next we'll see the signal distortion. Next class we'll see it. I'm giving the hints. Signal distortion here actually, I told you if you launch some pulse within the fiber, then because of some factors, we'll see what are the factors. Either pulse will be broadened or can be narrowing of pulse will be there. Generally, if the moderate intensity of light is here, I mean not too intense, then you see the pulse shape is broadened. So you see it here. It is very narrow. If it is broadened, then its data rate will be degraded, right? Because of this propagation. Suppose if you some data is there at 10 Gbps, you're propagating through the fibers. At the end, you will not get the 10 Gbps. It will be reduced. Data rate will be reduced. Because you see this pulse shape will be broadened. So ultimately, they will overlap, and you will not be able to recognize the original pulse. So that is actually the signal distortion. Means after a certain distance, a certain length distance, the signal distortion will be too much. So data rate will be degraded. Right. We'll see next time. So that is because of actually the variation of board velocity, and those are called actually dispersion effects. So next time we'll see the dispersion effect. And that will cause actually the signal distortion in optical fibers. So till now, if you have any questions, anybody you can ask any questions. What's about then? If you have any question, you can ask. No one if else you are nobody else is asking any questions. So if you have any doubts, you can ask.
No, sir.
One thing just I have forgotten to mention, if you see the spectral attenuation curve, the minimum loss occurs, you can see it at 1550 nanometer, where infrared tails cross intersect the Rayleigh curve. It's a Rayleigh scattering loss. Oh, okay, this I have forgotten to mention. This is the dotted. This dotted one is the Rayleigh distortion curve. Rayleigh scattering curve. Rayleigh scatterings. Rayleigh scattering. I've seen that Rayleigh scatterings. These are Rayleigh scatterings. The particle size less than equal to lambda by 10s. Rayleigh scattering. These are Rayleigh scattering. This is the UV tails. This is infrared tails. So it is the intersection of Rayleigh curve and the infrared curve where the minimum loss you can have it. Minimum loss, right? And this is the net loss curve. You see, this is a net loss curve. So, hinge is there because of these wireless lines. So maximum peak will be there, and this here. So this region is the minimum loss around 15. That's why present day communication it is around 1550 nanometers. Because in this case, loss is also we'll see it. We can design the fiber so the dispersion also will be minimum. That's why another class of fiber will be that is called dispersion shifted fiber. Anyway, these points you keep in mind, and this will be helpful for your either quiz or for this answer point of view. Okay, I'm stopping these ones. If you don't have any questions, thank you. Then any other questions? Okay.